All right, thank you guys for coming. Congratulations, you made it to the last track talk, so made it all the way through. My name is Michael Bouchard. I'm a PhD candidate in planetary science at Washington University in St. Louis, where my focus is Martian materials and processes. But I also have practical experience and graduate certificates and degrees in geology, geophysics, and systems engineering. Today we're going to shift back and talk about Mars. I loved our last couple of talks. They were great. But thinking about the logical precursor to the next mission to Mars. And we'll kind of explain what this is all about. Real fast, I want to take a moment and thank you all, the Mars Society. A lot of where I am in my career trajectory as I am today is a result of activities that you guys supported. This was one of the Mars Desert Research Station missions. I was the crew geologist discovering cross-bedding on Mars, which was pretty exciting, evidence of water. At my undergraduate institution, Missouri University of Science and Technology, I also started a Mars rover design team that our first year took dead last place. Barely even moved. Yeah, you got to start somewhere. Exactly. But we learned a lot and came back 1 year later and took second place in the world and first place of the US teams. And it was a great experience and has launched me and many of my colleagues into careers in aerospace, planetary science, people working at SpaceX, Boeing, all those things. So thank you. We've heard a lot of really great talks this week from all kinds of different perspectives about Mars, about technologies that go along with making these Mars missions happen, about the interesting science, exciting questions out there, and a lot about the big challenges that this problem of sending humans to the red planet gives us. However, though, you can almost feel the tide starting to change. Gears are starting to move. It's a very exciting time to be looking at Mars right now. We had speaker, a congresswoman, and a representative from the Senate Space and Technology Subcommittee staff both talk yesterday and telling us how much bipartisan, incredible in this day and age, bipartisan support there is for space technology, human missions, and even sending people to Mars. That Senate bill, which is actually offering more money than even the presidential's procurement bill recommended, just passed. And so now it is happening, and it's in the writing that humans to Mars is on the journey. And as NASA likes to brand it, hashtag Journey to Mars. You know, in the 2030s, we're going to send people to the Mars area, whatever that means. And it's going to happen in the 2030s. And that's, yeah, Mars-ish. But that's really exciting. But if that's going to happen in the 2030s, that's just around the corner. So we need to be starting now to make that happen in the 2030s. So what I'm going to be talking about. So is that possible? Well, just a quick little point. 1903, Kitty Hawk, the Wright brothers have the first powered, manned, heavier-than-air recorded flight. Incredible jump. But only 66 years later, humans walked on the surface of the moon, a body that we'd been staring at for thousands of years, wondering what it was, where it came from, what it's made of, and how old it is. Questions we answered by bringing back pieces of it. Well, 66 years from this anniversary would be 2035. So maybe that is within that realm of possibility. So if we're committed to doing this in the 30s, how do we make that happen? So the objective of this sort of presentation is to present one possible strategy for how we might get humans to Mars in that time frame, given the technical, medical, economic, political challenges that currently stand in our way. And the position I'm going to propose is that we've heard a lot of great ideas, a lot of great mission plans, a lot of great strategies, technologies to develop. But what if we zoom back a second and take a look at it from a programmatic perspective, looking at it from an entire program of missions? So what are some of the challenges? There's two camps. Yes, there's the lunatics and the Martians. That's a known camp. But there's also two camps who argue, we know everything we need to know. We can go today. Just say yes and let's go. And there's the other camp who says, well, the more risk-adverse, there's a lot of things we don't know, things we don't have constrained, problems we need to solve. And like with most things, the answer probably lies somewhere in the middle. But I think there's a way to appease both of these groups, because there's incredible professionals with great experience on both sides of the argument, and get their support for a program. We all kind of know where Dr. Aldrin stands in this, but I had to sneak this picture in somehow. I just figured this was the moment. Interesting connection. Some other challenges. Apollo 18, 19, 20, Constellation mission. Space is hard. It's really hard. And to carry out these really complex endeavors, it takes many years, 5, 10, 15, 20 years to execute a series of programs. And that can be challenging to remind the taxpayers and the governments that the cost that they're putting in, we need that support for a continuous period. It seems like every 4 or 8 years, the political winds change and things get canceled and things get redirected. And that is very challenging for programs that need more than 4 years to really get a job done. So that's another big challenge. Another challenge we're facing, people put this better than I, but that idea of building your architecture to get somewhere backwards. You set your goal, then you create your path to get there, working backwards, figuring out what positions, what questions you need to answer, what technologies you need to develop. And that is how a lot of systems engineering is done. That's how you develop the most efficient solution to an infinite design space. When you start to design something, there's an infinite possibilities of ways to do it. And one of the most efficient ways of doing that is by working backwards, as opposed to standing where you are and doing a little bit of this and a little bit of this, a little bit of this, hoping it'll take you in that direction. That's a recipe for inefficiency and higher cost. So these are some of the challenges we're working with. So how can we address these political, economic, technical challenges to sort of approach that? So first of all, let's take a moment and think about the last time we visited a planetary body. The human space program that got us to the moon. There was the Mercury program. Excellent program. Most concise way to explain its goal was put Americans in orbit, preferably sooner, faster than Soviets. And they did that. It was essentially strapping test pilots in tin cans on ballistic missiles, but they did that. That was the goal, and they did it. The Apollo program's express goal was to land Americans on the moon, and they did that. But kind of the unsung hero is the Gemini program. And I'm not the first one to make this connection or point this out, but what I really love about Gemini was the purpose of the entire Gemini program was to learn everything we need to know to plan the moon missions. For the first time, we were rendezvousing in space, docking in space, and navigating and flying around, actually controlling your spacecraft, things they'd never done before. You had multiple crews. You had people eating and sleeping in space for the first time. You had the first spacesuits and spacewalks, technologies that had to be developed, basically miniature personal spacecraft. We had missions that were the same duration as a lunar mission. To answer all of those questions, to get the engineers at the point where they felt they had enough of the problem constrained to design the Apollo architecture. And while this was going on, there was also the parallel program of the surveyor robotic exploration of Moon, impacting it, flying by it, taking pictures, impacting it, landing on it, making sure you could land on it. For a while, some people thought maybe it was just dust and you would just sink right through. These are questions you had to answer first. And by answering those questions in this program, they were able to design a successful Apollo program. So if the goal is humans to Mars in the 2030s, then your path to get there, working backwards, is some sort of Gemini program, some sort of collection of missions that identify everything that we're left wondering about. All those question marks at the end of these presentations. How do we answer all those questions? We can start by identifying knowledge gaps. So this is how much we need to know about variable X. This is how much we need to know about radiation, how much we need to know about low gravity environment on humans, isolation effects, how much we need to know about landing heavy things on Mars. This is how much we need to know about X. You figure out this is what we know, and this is the gap. This is what we need to figure out. These are the questions we still have. We can land a ton on Mars, but we're going to need to land 2, 3, 4, 5 tons on Mars. How do we get to that last step? So you begin to develop each of these categories, looking at each of these areas of challenges, and figure out what are those knowledge gaps, those areas you need to fill. Once you have those identified, you begin to figure out gap-filling activities. What do you need to do to answer all those questions? Once you have all those activities together, you kind of rearrange them and shuffle them into a set of missions. The idea is that when you complete those set of missions, you will have answered all of those questions, addressed all of those risks, and developed a lot of the technology you're going to need for that mission. Some of the key things here is that, remember, apparently, there's politicians in Washington who want this to happen. There's a lot of public support for people who, when you ask them, do you want to go to Mars, they want it to happen, but none of them are willing to sign that check yet. Well, this is one way to make real progress towards that at a much cheaper cost. The cost of a type of gap-filling missions like this would be far less than a full Mars architecture. And it would satisfy the people who want to go now because we're making real progress, and it would satisfy the people who say there's lots of risks to mitigate because we are mitigating and answering those risks. Another key point of this is that it should be completed in 8 years. One political season, let's call it. One administration you can get through from start to finish, cohesive umbrella, entire mission, that at the end of, you can step around and say, look, what's next? We go to Mars. It's the only thing left to do. So this is kind of in the abstract. So let's take a moment and create kind of a case study. Let's do a quick version right here, very high level still, but kind of walk through so we can make it a little more concrete, so we can kind of think about how this might actually look. So I just, and let's call it the Atlas program. Because we're PowerPoint engineering, everything's going to work. We can call it whatever we want. So let's just go ahead and call it the Atlas program. So let's think about getting to Mars, the things you have to do to get there. Getting off Earth, we're pretty good at that. We've kind of, figured that out. Getting to Mars, we've gotten pretty good at that. We can get there with plenty of robotic missions. Getting to the surface of Mars. Right now, the percentage is still 2/3 of every attempted landing mission to Mars has failed. But in recent history, the numbers are much better. We've learned, and we've gotten better and better and better. Right now, the Jet Propulsion Laboratory is the only one who's done it successfully, but more and more people are willing to try, and it's something that we've started to be able to do. Surface operations. What do you do when you're down on the surface? We've got some great experience with the active rover missions, delayed communications. We've got the Apollo heritage and things we've learned from that planetary human mission and analog missions. But we really need to nail down command communication architectures, GPS and localization, big questions that we still have to answer. Ascent from the Martian surface. We understand the physics, but we've never really done it. Getting back to Earth, we haven't done that yet. And getting down to the surface of Earth. We have some experience with ballistic re-entries from the Apollo program, but again, we haven't really done that in a while. Now, the Earth transit back, if you leave your vessel in orbit, it's just a matter of fuel. It's kind of the similar problem. But these are sort of the areas that we need to focus on to create that list of challenges that we need to address. So I went ahead and just picked 13 challenges that represent things we need to solve for the Mars mission. It's not exhaustive. There's certainly more, but just for this case study, let's focus on these 13. The transit, equipment, environmental systems, radiation protection. How do you get your flesh bag safely through the vacuum of space to the other planets? Galactic cosmic rays, solar energetic particles. This is a radiation problem, particularly in the transit as well as on the surface. Prolonged exposure to low and lower as well as microgravity environments, what that does and how you mitigate that. Landing things heavier than the 1-ton rover that we've landed. Landing on Mars is really difficult. It's like the worst possible combination of atmosphere and it's just enough that you can't just bump into it with a spider-looking thing, but not enough that it'll really slow you down. So it's really challenging. Mars ascent capability, getting off the surface. Inaccessibility of terrestrial medical facilities. The longer your mission becomes, the more likely you have a possibility of a catastrophic failure going wrong, the more likely you are to need on-site medical care and field equipment to address it. Equipment failure, spares. The MIT team at the last Mars Society conference made a good point about the rising costs of and rising mass of replacement parts as things break down. Sustainable engineering. Forward contamination, back contamination. We'll have to come to some sort of agreement here to make progress. Consumable dry mass, the massive amounts of fuel and food and water and atmosphere. What can you do about those challenges? Prolonged effects of isolation, cultural stressors in case you have a multicultural, multilingual crew, and the excessive costs. So these are some of the challenges. I've gone ahead and organized them into 5 categories. We have technical problems that are more engineering problem solutions, physiological and psychological things, human factors, political challenges. The terrestrial medical, medical facility problem is kind of a combination of technology, training, those sort of things. So these are, for this case study, some of the challenges we're going to think about. So the next thing you do is you look at the knowledge gaps. What do we know about each of these? And what do we need to know before we're confident that we could sit down and commit sending humans there? We don't have to read all of this, but just the idea of thinking, where are we, for prolonged exposure to low gravity environment. We have great history of the International Space Station and everything we've learned from that. What we need to do is kind of extend it to thinking about 1/3 gravity and what that would do to the human body. What is 6 months plus a year of 1/3 gravity plus 6 months in space do? Terrestrial facilities, you can look at Antarctica. That's a very kind of good case study of where you have a very isolated facility that is operating with really big sort of medical challenges, and you have to have sort of these field equipment. And then you can start to put together what sort of gap-filling activities will you need to do to fill all of these uncertainties. Once you have these, you can kind of start to come up with ideas for missions. What sort of missions could you do that would address these? For example, a Mars flyby mission, whether it's 2 people, like Dennis Tito's Inspiration Mars, or 6, like Lockheed's Mars Base Camp. Sending humans to orbit Mars would address each of these challenges. You'd have to design solutions for these challenges. A Arctic or terrestrial somewhere simulation, high fidelity, very high realistic, basically trying to build an entire Mars base, but just on Earth would address a lot of these. Robotic Mars sample return would address a lot of the problems. Ascent from the surface, return, coming to an agreement about contamination, as well as being the holy grail of planetary scientists, Mars scientists. In situ resource utilization. This strategy addresses a lot about your consumable mass, bringing down your fuels and your water that you have to bring with you, as well as the cost, because mass is money in space. And then the artificial gravity problem. What do you do about that? So if you had a mission for each of these, you could address all of these challenges. But we've got 5 here. Maybe we could kind of condense it a little bit. So what if we have a human Mars flyby mission, a terrestrial simulation, analog, robotic Mars sample return? But what if we, on that sample return mission, put in some beefed up ISRU testing? MOXIE is going to fly on the 2020 rover. That's really exciting. But before you send humans to the surface of Mars and tell them that they're going to make their own fuel to come back, you bet somebody's going to have to make sure that they can actually recombine those materials into a fuel. Maybe you could do that for your robotic mission. The artificial gravity problem, maybe that could be part of the things studied on the transit mission. Put up a tether, separate and spin them up, generate some levels of gravity on your transit or in orbit. And now things kind of start together. You have 3 missions under the umbrella of 1 program, together addressing all of those problems and answering all of those questions and making real progress towards actually having a Mars program. One of the important things to remember is that we want to try and diversify the participants. Even within NASA, for example, the robotic scientist Mars exploration program and planetary scientists would love to do a sample return mission. HEOMD would be, more responsible for the transit mission. And if some unnamed program were to go missing in the next couple months, maybe this would be a great way to fill that. So if you diversify those, people are more invested in it, and it's more likely to get support. But not only within NASA, in diversifying your partners beyond that, your industry partners. Is this transit mission using SLS and Orion, or is it using Falcon Heavy and Red Dragons? As well as involving other community members, academics, and support groups and interest groups. The Mars Society, all of their experience from the Arctic Flashline analog habitat that they're putting up. These are real contributions that everybody can make to make this all happen. Since this is, kind of a very high-level look, I'm going to throw up a couple of numbers. They're very hand-wavy. If this is your wheelhouse and you have more information, I'd love to talk to you afterwards. But just so we can get a little bit of perspective, let's say $5 billion for a mission. The Gemini competition next door is going on. They've listed numbers from 1.5 to 20 billion. So let's go with 5 billion, considering the heritage already developed for some of the heavy launch vehicles and capsules. let's say 6 billion for a Mars sample return. 2.5 was what it took to get Curiosity to the surface. This is going to be a heavier mission, newer technologies. So this is a little bit out of the class of the planetary science flagship mission, but it's still kind of within that range. And let's round up to $1 billion for the Arctic simulation. So that's $12 billion. It's a lot of money, but remember, this is over 8 years. And it won't be allocated exactly in segments every year, but you could pitch it to someone as an average of $1.5 billion per year. This is money we can actually foreseeably, I can conceive convincing and having conversations about trying to get this money out of Congress, this amount of money. And it might even be a lot less than this, especially if you think about areas within NASA that are already working on parts of this or would incorporate this into their current operating robotic or human mission budgets. That number can be brought down, as well as some of these are kind of overestimates. So this is money, so this type of program could be done for much cheaper, could be something we could encourage people and get them to sign on for, just getting a little bit more. Maybe we can make that 1% of the federal government budget for NASA. This would be well taken care of. And it could really happen. But not only that, think about where you are at the end of this mission. 8 years have passed. You've had a very exciting, and the 8 years is also important not only from a survival perspective, but from a focusing perspective. Keeping everyone, keeping the technologies being developed fast enough so that you're not outstripping with new technologies and having to redesign everything. Keeping people motivated and keeping the public interested. It'll get people excited about it. It'll get everyone on board from both the camps of going now or going later. And when you're done, you'll have answered all the questions and developed a lot of the hardware. You could leave this transit vehicle in orbit and maybe reuse it. This would be a training facility for the Mars astronauts once they start doing those missions. So this could be a programmatic level that would get us to the point where we could commit to doing the Mars mission. They're within what I call our technical horizon. These are technologies that are not quite developed, but we could realistically sit down and start doing preliminary phase designs for these sort of things and testing. Addresses all those knowledge gaps and could be completed by, if you put it down on the incoming president's desk, could be completed by 2024, or if you put it down on someone coming in 2020, 2028, that sort of time scale. So real fast, next steps, what does this look like? Identify the knowledge gaps. There's some really good work that's already been done by this. The Mars Program Exploration Group and the Small Bodies Exploration Group had a really big conference. It was really exciting, and they did just that. I didn't know that while I was doing this. I went and looked at theirs, and we actually agreed on a lot of things. So identify those knowledge gaps that need to be filled. Figure out those gap-filling activities. What are the specific things you could do to fill those gaps? And there's some work starting to be done on this as well. Then you integrate them into a programmatic level architecture. Again, this was just my example of how you would do that, keeping in mind the low cost and the 8-year budget. Sell this program to your key demographics, which hopefully, if by creating the program and architecture you included people in that conversation the entire time and had them involved, they're already bought into it. This is not just people like NASA administration, NASA centers. This is industry partners. This is academics. This is interest groups. This is the public. This is key Congress people and senators. If you have all those people on board as you go through and develop this plan, by the time they're at the end, hopefully they'll be in agreement with the plan and already ready to support it. And finally, obtain the commitment and then do it. Just sort of, you can make it happen. I really think that, taking a level to sort of a step back and approaching it like this and keeping it under one umbrella and one brand will kind of give it that cohesive vision and that complete approach to answering those questions of how do we get people to Mars by the 2030s. I personally like just calling it the Atlas program. The idea is that upon its shoulders, you will build the Human to Mars program. And on that, I just leave you with a quick quote from Herman Melville, author of Moby Dick. "I'm tormented with the everlasting itch for things remote, to sail forbidden seas and to land on barbarious coasts." And thank you all. I'll take some questions. Go ahead.
A couple of things. I think that you could do the Arctic simulation using the Flashline Mars Arctic Research Station, perhaps upgraded, probably for as little as 10 million or less, I would imagine. That's just one thought. But I'm interested in the idea of a Phobos Deimos mission, and I wonder if you think that that would be superior to a Mars flyby, because you would additionally test a Mars orbit insertion and that's the transinjection as well as getting
Mhm.
the great science of visiting Phobos and Deimos. Do you think that would be a good idea?
Yeah, I really liked the Mars-based idea of having those sorties out to Phobos and Deimos while you're doing it. There is some great science you can do there, and I would definitely think a Mars flyby would be more beneficial if you did go into a capture orbit and then an escape orbit with all that mass. That would kind of be key. If you just look at the baseline, what do we need to understand to have humans survive on the surface of Mars, I don't see a technical value from going to Phobos and Deimos if you're already in orbit. And plus, the orbits of the moons are pretty equatorial, and they're not really the same type of orbits you would leave your habitat in. But there's science to be done there also.
Just a thought, but I mean, would you think it would be reasonable to sort of do even less missions and combine the sample return with the orbit mission, where say the sample return machine is sent from the orbiter, and then I don't know how long that would take to do the actual sample collection and launch via ISRU, but then once the samples are collected, then it's launched back up to the orbiter at the appropriate orbit. Or do you see more value in splitting the two?
No, that's a good question. Can we combine these even further? An architecture I've heard proposed before is, you send your sample return mission, but its capabilities just to Martian orbit, and then a human crew vehicle would arrive and collect it and bring it back, which would be a good way to merge those. I think that's definitely an option, something to explore in the trade space. One thing, though, that Steve Squires says in his book Roving Mars, where he talks about the Mir rovers and their mission, was that sometimes you do have to be willing to do 80% in order to go at all. If you always try and get 100% of everything, sometimes that means you just get cut and you don't go. So you might have to, so that's why I kind of like diversifying it a little bit and kind of mixing the pots so that more people have investments, more jobs, it's more security. But that's, I think, that's a great, thing to examine in the trade study. Over here, and then
So great presentation. I really liked your cohesive framework for figuring out sort of the path forward to create and program before we go to Mars. Your 3 missions did not include going to the moon, which our previous presenter and Buzz Aldrin both think we should do. So what would you say to those 2?
that's a great question. To start off, I will say this is one of the key questions that will need to be answered in a full trade study. There are incredibly competent people on both sides of this argument, and they make good. We had Art Harmon gave a presentation just a couple ago, giving arguments for the moon side of things, and he had some good points. Personally, though, I'm not convinced that we need to go to the moon, and I'll tell you why. If you think about environmental, like Mars is about 1/3 Earth gravity, and the Earth is about 1 gravity. The moon's about 1/6 gravity. It has almost no atmosphere, just a light exosphere, where Mars has a very thin 1% thickness carbon dioxide atmosphere. So a lot of the surface processes and surface environments you encounter on Mars are more like things you can find on the Earth than they are like the surface processes on the moon. For example, the dust problem is significantly different. The electrostatic charging in the dust on the moon environment is a really big problem. But on Mars, it can be dust that accumulates on the rover's solar panels can be blown off by an extremely light, with that 1% density wind. So my argument is that if you work from the back, and again, this is something that people with higher pay grade than I will need to decide. But after you do a full study to evaluate, but in my assessment so far, if you work backwards and think about what are the technologies and how can we most efficiently solve them, I think there's a lot of areas on Earth that are as good an analog for Mars, if not better, than the moon is as an analog for Mars. But that's just my assessment. So.
Yeah, there's some interesting science going on at Mars now, such as blueberries might have been formed by lightning strikes at the surface. There's unexplained glow phenomenon, which might be nothing. And we had a comet show up as soon as Maven came in. Do you see that the science being developed at Mars is developing gaps in our knowledge or filling gaps in our knowledge?
Oh, you.
Generating new ones.
Both.
Whenever you look closer at something, you find out more of what you don't know. So I think that's great. You know, the more we learn about the planet, the more we realize we need to learn about the planet. But I don't think that should stop us from going.
No, of course not.
Yeah. So.
I just want to take a moment real quick to let anybody go that needs to go to get ready for our dinner tonight. But I know that Michael's probably willing to stay extra to answer any more questions that anybody